Today we're going to be talking about longitudinal techniques, and this is really one of my favorite lectures. This is one of the reasons I wanted to continue doing quantitative methods. We're going to look at some complicated figures, and I'm going to start with this one. And this is one of the inspirations that I had when I first started working quantitative data. This is Jackie Person's data. She runs a psychology clinic in the San Francisco area. What she does with each patient, she measures them frequently, and not just at the beginning of therapy, but every week in therapy. So this is one of the measures she gives. This is the PANIS. It measures positive and negative affect. This is the positive affect part of that scale, and it's not necessarily the opposite of depression, but we can think of it as being happy almost, and so this is, maybe that's an oversimplification, but when we look at this data, what we see with this red line in the middle is that's the average of where everybody's at. And on average, people are getting happier across therapy. And on the bottom, we've got the number of sessions. So I cut it off at 26, but there, some people went longer, some people went shorter, but people are getting happier over the course of therapy, which is great. When we look at the data more closely, we see these individual trajectories, and these are estimated trajectories. Each person is fit with an individual regression line. We'll get into more details of how to do that throughout this lecture. But what we can see are some interesting artifacts going on, or individuals happening. So we see this person right up here starts off one of the happiest people to come into therapy, and over the course of time becomes the least happy person in therapy. So what's happening with this person? There are a few individuals that are just going down over time, and we see these sort of trajectories where they're becoming less happy across therapy. The average doesn't really show what's happening for those people. We also see some people who are doing quite well in therapy. This person here starts off right in kind of the middle of their happiness, and just in a few short sessions, they're off the chart happy. So within 6 sessions, they're super happy. We also see some other super responders that are kind of moving up quite a bit, much more than the average trajectory of happiness. And we see quite a few of those sort of super responders that their happiness is improving much more than that average line. So the average line doesn't really show them or display what's going on for them. So the average is useful, but it doesn't necessarily highlight one person or highlight what's going on for everybody in therapy. So that made me want to continue going down this path of individual differences in quantitative methods. I'd like to start with this quote from Benjamin Franklin. I just like this. Is when you're finished changing, you are finished. And really, when we're studying clinical psychology or psychology in general, we're studying change. We want to see people change, or the lack of change, the lack of adapting is important. So this is vital to really measuring what we want to do in therapy. So when we look at this longitudinal research, what I really want to do with this, these are things that John Nesselrode has talked about. What we want to measure is within individual change. So how does the individual change over time? And the behaviorists have talked about this as being the only important thing in looking at change, or maybe not all behaviorists, but they want to see how an individual change. So when we do a behavioral therapy and we create an intervention, we want to see how does that individual change, and that's what's really important. In more experimental, we've lost that within individual change, and we'll get into that in more detail. We want to see how the individual changes, and then we also want to see how people change differently. So what's different between individuals in their change process. So this is what we're aiming for when we look at longitudinal methods. So let me go over some important advantages of the methods we're going to talk about. We're going to talk about repeated measures first, and these are not necessarily advantages of repeated measures. So what we want to do is to be able to have everybody on different cadences or different timings. So imagine somebody in therapy. You might aim to have them to come in weekly, but maybe somebody needs to come in 2 or 3 times a week. Somebody with anxiety, you might be working on more of an accelerated plan with them. We want to be able to measure that change process. And so the cadence of when they come in or when they're measured doesn't have to be the same for everybody. Repeated measures can handle different timings. It just assumes everybody's on the same pre-test, post-test, 6-month follow-up. But they have to be at those timings. We might, if we're doing a developmental study, we might want to get kids in the fall, but maybe some kids are measured in September, some kids are measured in November. We want to be able to highlight the differences in timing. We might not have everybody with the same number of measurements. We might have, some people in therapy especially. We might want to have people every week for 8 weeks, but that's, we're going to have people miss a week. We're going to have people quit therapy. We're going to have all kinds of situations that happen. So we need to be able to look at data that doesn't have every time point, and maybe even just one time point. That can be very informative with one time point. We want to be able to pattern nonlinear data, so we can look at things that are changing differently. We think about therapy data. People aren't going to change in a linear pattern for their depression, that they change exactly the same at the beginning that they do at the end. We want to look for those bursts of change. So thinking about this is a study we did with Phil Kendall's data. This was looking at Coping Cat. It was a family-based treatment for kids and adolescents with anxiety, and the therapist, the mother, the father, and the child all rated how their alliance over the course of therapy. And one of the challenges that was presented to Phil Kendall and his team was, when you start doing exposures, alliance is going to drop. And that was, an idea that many people who talked about exposure therapy suggested that alliance would drop. And so what we wanted to test this. Do we see a different pattern and change when exposures are brought on? And because this is a structured type of treatment, we knew that exposures are brought on right in this middle part of therapy. So we set up a different type of curve. We allowed for alliance to change differently at the beginning of therapy and again once exposure started. And what we saw in the dark line here, this is the Coping Cat treatment, and we see no decline in alliance. Alliance stays relatively flat over the time once exposures start. So we didn't see this decline that people thought would happen. Once the child would start going through exposures, the therapist might look like a bad person, and that didn't happen. And in the gray line, we have the control group, which is an educational support group, and we almost see a decline. I'm trying to remember if this is significant or not, but in mother's rating of alliance, maybe the mother thought this isn't working very well and started to think that the therapist relationship wasn't going as well because the symptoms weren't getting any better. So we didn't see this, and we wanted to pattern change differently. All right. Some other things that we want to include in these type of analyses are time-varying predictors. So when we're predicting change, there might be things that are happening at the same time that might be predicting the change. And we'll get into this in much more detail in the next lecture, not necessarily today, but we're going to look at how these dynamics change over time. So what needs to change first, and these different patterns. It's not just one thing changing at a time. Sometimes multiple things need to change. And then also interactions that might be adding to the change or taking away from that change. Some challenge of these longitudinal studies and things that we're hoping our methods can overcome, and this is just a challenge in general, is just practice effects. Do we see when people are taking the same measure multiple times? Do we see a practice effect or some sort of carryover? The observations, because it's the same person measured over time, this is actually going to be an advantage of longitudinal, the methods we're going to use, because we can see those individual differences. We can pull that out and look at it. Attrition, In repeated measures ANOVA, if people go missing, they're deleted from that data. They can't be used anymore because they don't have all data points. We're going to be able to look at attrition and see if that's important or not, and see the patterns of people who leave early. And this is the same thing with missing data. If a person's missing session 2, out of 8 sessions in repeated measures ANOVA, that person can't be included in that repeated measures ANOVA data, but in other methods that we'll talk about today, they can be. And then also that time varying covariates is what I mentioned. We'll get into that in the coming weeks. So we're going to talk about repeated measures ANOVA, multi-level modeling, and latent growth curve models. Multi-level modeling we'll get into more detail in a lecture next time. But latent growth curve models I'm going to actually go into first. Repeated measures ANOVA, I'm going to probably say some bad things about it. And, you know, it can be useful in certain situations. And one of those situations might be if you have the timings exactly the same between each time point and you have no missing data. So that might be a time where repeated measures ANOVA could be useful, and maybe the data is pretty homogeneous. You don't have a lot of individual differences that you really want to find. Again, we can handle missing data very well with repeated measures ANOVA. We can have variations in timing so that people are measured at in different waves. We can have time varying covariates, and any sort of predictors we're going to look at have to be categorical. So if we want to look at a group difference over time, it has to be categorical. You're in one group or another group. We can't handle different amounts of anxiety. We have to break it into low and high amounts of anxiety for those group effects. And basically we can only look at fixed effects. All right, so let me go into repeated measures ANOVA in a little bit more detail. The data we're going to use for today is some WISC data, and the kids in this study were measured in 1st grade, 2nd grade, 4th grade, and 6th grade. So I see here I got a little typo, 4th grade, 4th grade, and 6th grade. So in this chart, these are the means. We're using the raw score for performance data in this data, and what we have here is 1st grade, 2nd grade, 4th grade, and then 6th grade. And you see this is an output that comes with repeated measures ANOVA. And with repeated measure ANOVA, it treats each of these intervals exactly the same. So in this first interval here, we have a 1-year interval. The second interval here, it's the same distance in repeated measures ANOVA, but that's a 2-year interval. And same thing here, we've got another 2-year interval. So repeated measures ANOVA doesn't account for these differences in these interval timings. And there could be, if we're looking at a growth model, we're only applying linear growth here, but that could be some other type of growth pattern, a nonlinear pattern. So that's another issue we'll have with repeated measures ANOVA. Without going into the details of calculations, if you remember, the ANOVA had an F ratio. We had the numerator of that F ratio, which will be pretty much the same in repeated measures ANOVA, and then we had the denominator. And in the denominator, we throw away, we don't use the error associated with individual differences. So the denominator gets smaller, which helps the chances of that F ratio being significant, but we're throwing away all those individual differences. And I think those individual differences are useful to look at, and rather than just throwing them out. So that's another disadvantage of that repeated measures ANOVA. And then when we look at the results of this, and I'll just show the results to kind of highlight what we'll be seeing later on with the other types of methods, we have different corrections if there's sphericity issues, but they're basically all the same sort of result. We have a significant F ratio. We have change going on in this model. So, all right, and what repeated measures ANOVA does is it basically creates an average line. And I'll just kind of show this in this formula, and I think this formula is actually useful. That's why I'm going to go into it. So for any for an outcome measure, and this we're going to use the WISC score for any individual. This I here stands for individual. That individual is predicted by an intercept and a slope plus some error associated with the individual at each time point. So that kind of makes sense. This is a line for each individual. However, when we start to break this down a little bit more, when we look at the intercept, so if we take this here and break it down for repeated measures ANOVA, they're going to get their own individual intercept. So that I stands for an individual. They get their own individual intercept, which equals the average intercept for everybody. So it was kind of a trick. A person, let's say child A, their intercept is going to be right here where the average is. Their slope is also individualized, and if I break this down, their slope is the average slope for everybody. So basically each person is said to equal this average trajectory for everybody. And that's where we're throwing away those individual differences. Here in this error term, the individual differences are there. We can also add group effects. So we add what group the person is in, and we get two different trajectories. I'll go into group effects in a little bit more detail. So again, here is our average trajectory for that WISC data, but it's superimposed on individual trajectories. And this is pretty homogeneous data, so it's not going to be all that interesting when we get into it in more detail. But we can see this person starts up at a raw score of 46 to begin with, and kind of stays and kind of grows with that. Their intercept is very different than the 19 that is created by the average. We also have some people that are starting off at a very low number and stagnate over time. So again, their intercept is very different from this average intercept. Their slope, this person's slope here, if I could draw a straight line, is pretty flat compared to this average, which is going up over time. Another thing to note on this slide is when we start to use these more advanced methods, our intervals are going to be correct. So this is a 1-year interval. This is spaced out a little bit more. This is now a 2-year interval for between 2nd grade and 4th grade, and then this is another 2-year interval between 4th grade and 6th grade. So our intervals are spaced out correctly when we use these other methods, and that's what I'm demonstrating in this figure, which comes from the other methods. All right, before we get into those better methods, and I stop bashing repeated measures ANOVA, let's talk about getting to know our longitudinal data, and we really want to understand what is happening, and there's a lot of techniques to graph it. I'm not going to go into all of those techniques today. I've got some syntax for you for that. But when we look at longitudinal data, we have to think about how our data is formatted, and that's going to be pretty important. Most common way we do this is what's called the wide format. We'll see this in SPSS quite often. Each person in the wide format gets their own row. So this is person 1, their WISC performance score, and this is an older WISC where it was broken into verbal and performance indices. So a performance score, raw score at time 1 for this person is 19, time 2, 22, 4th grade, 43, and 6th grade, 44. So that's one person per row, and we can see person 2 in a row, person 3 in a row. So we use this wide format in SPSS. If we're doing repeated measures ANOVA, we'll use wide format. When we use latent growth curve modeling, we'll also use this wide format. So this is probably what we're used to. For other methods, and when we're exploring the data, we'll actually want it in a different format, which we call long format. And so each time point gets its own row. So here's person 1. They have 4 time points, so they get 4 rows of data. This is their performance score in the first wave. This is their performance score in the second wave, or and then et cetera, et cetera. So this is a second grade, fourth grade, sixth grade. So for each time point, they have their own row. What I've got here, years, I'll talk about this in a few minutes, but we're going to center the data. We're going to make it so that the first time point is at 0. And what that does is it's going to make our intercept at that 0 time point. So I'll explain why this years and these waves are here, and why the numbers aren't matching up to grade, which I could have another column of grade, which would have probably been a little easier. So we'll want to go back and forth between this wide and long formats, because the long format is really useful for creating graphs. And when we go to multi-level modeling, the wide format's what we use in growth curve modeling and in repeated measures ANOVA. Today we're going to stay in just the wide format, and but when we need to convert it, there's a few ways to do this. It's relatively simple to do it. So we'll go to our data command in SPSS and restructure, and we'll just follow their directions. They actually show these nice little figures where it shows from a wide to a long, and it's actually somewhat intuitive to do. I tend to use syntax quite a bit, and with the syntax is relatively simple, and you just will have to change your variable names. The other thing I put here, this last is what I'm going to talk about in a minute. This is where we center the data and where we make the first time point equal 0. So this is a graphical representation of what we're doing. So what we really have, our figures are based on kindergarten, or I'm sorry, let's start this over. There's no kindergarten in this data set. So the first time point is first grade, second time point is second grade, third time point is fourth grade, and the last time point is sixth grade. So if we were to really put this on the original scaling, which is grade, these are our time points. That text looks really nice. So grade 1, 2, 4, and 6. And we can see the spacing between these intervals is correct in these figures. We want, in these methods, to move that scaling over so that the intercept is at 0. And what that allows us to do when we're looking at the intercept, we know that that is where time point 1 is. And so we see the intercept score, we know this is the average where everybody started. So this is centering at the very first time point, and at grade 1. This is centering in the middle, and sometimes this is useful if we're trying to find where the intercept is, where in the middle of therapy or the middle of things, we might center in the middle. This isn't used as often. And then sometimes we center at the last time point, where people end. So that intercept, when we look at the intercept value in our output, this is the point where people end, and that could be important too. So I think this first method is what we're often doing. So the intercept is at the beginning. Sometimes the intercept is at the end, and that's used slightly less often. All right, so I'm going to talk about multi-level modeling and latent growth curve modeling. I'm going to mostly talk about latent growth curve modeling. And the differences are really just in what software you use. There's going to be some fine differences in how we set up the time intervals and some other things. I find latent growth curve modeling is the easiest to do. Some of you might find SPSS is a little bit easier, or multi-level modeling is easier because you're using SPSS, but it's basically doing the same thing. So we're going to go into latent growth curve modeling in more detail today. Let me just show you, though, some of the figures that we're talking about. And whenever we're doing this, I showed you the formula for repeated measures. And with repeated measures, we had a individual trajectory, which was just set to the average. So everybody was set to this red line in that figure. When we do these models, multi-level modeling or latent growth curve modeling, their intercept, it's individualized. And when we break down what's happening, we have the average plus some individual adjustment. So the individual is adjusted from the average. So that gives everybody their own starting point. And I'll show you that in a figure in a second. We also have the slope is individualized. So if we look at the slope and we break down what's happening with the slope, everybody is based off the average slope, plus they get an adjustment based on themselves. So they can have a higher slope or a lower slope or more blunted slope. So everybody is adjusted based off of this average. Everybody gets their own slope. So what we see in this figure is we've got everybody has their own starting point and their own slope. So some people are really close to that average slope. Some people have a negative slope, so they're taking away a lot from that average slope. Some people have a larger slope, and so each person gets their own trajectory. And that really is going to be important when we start to look at why things are different for different people. All right, we can also do the same thing with groups, and we can start looking at different types of treatment. This will get into more detail in latter lectures of looking at treatment effects and other predictors of treatment outcome. So let me just show you this in the graphical format. Again, this is our formula that I just went over. This is with our whisk data, and what we see here is this intercept being represented down here, and it's represented by an average intercept. So I've got that in this figure shown here, plus this individual component. So for this person up here, they're starting a lot higher. They're getting this much added to their intercept and to the average intercept. So for this person here, their value of this error term or this individualized adjustment term is about 22 units or so. For another person, it might be subtracting out 19 units. So this person down here is much lower than the average, so this would be a minus 19. So everybody gets their own intercept. And I'll just kind of show you in here, kind of breaking it down. This is the average intercept, and then this is that individual adjustment. So how much different they are. So for this person here, they're getting 22. This person here is getting a 22 point above the average intercept. So I think that hopefully makes sense and hopefully is interesting. The slope is also similar. So we have the average, or the slope is individualized. It's made up of the average slope plus some variation. So here we've got on the figure, we've got our average slope. This is pretty homogeneous data. Most people are pretty similar slope-wise. There's not these extreme going up and down. People aren't losing intelligence scores. So with intelligence data, it's not as interesting as sometimes with therapy data or depression data, which is going up and down for different people. But we have some people who are maybe, I lost a person, this isn't all the data, but we had a person that was pretty blunted, that had a sort of really slow slope. They didn't change much. And if that person were actually in this figure, you would see their slope would be a minus. They're getting subtracted off of this. We've got these people up here which have a little bit steeper slope than the average, so they're getting a additional adjustment to the average slope. So again, everybody has their own intercept and then their own adjustment to their slope as well. Okay, so we can use latent growth curve modeling, and if we think of confirmatory factor analysis, basically the intercept is something we wish we could measure, the average intercept, and the average slope is something we could we could measure. So those sound like circles when we bring it into structural equation modeling terms, so we could create these factors. And if we look at this, we're going to get into the details of this figure and get into it in much more detail. But if I put the timing for this equation here, and instead of years, I'll just break it down. We have a time point where they're in first grade, which I'm labeling it time point 0. I'm centering it to 0, so that is the intercept. Second grade is time point 1. Fourth grade is time point 3. And then sixth grade is time point 5. And the reason they're off a year again is because I bumped everything back a year so that the first time point would be at 0. And if I take this equation, I can basically chart this with two factors. So we have a intercept, and we multiply that intercept by 1. So our factor loading would basically be 1 at each time point. So so this intercept becomes a factor. And now that I look at this arrow, I have to adjust this. This arrow should point here, and this arrow should point up here. This intercept, everything is multiplied by 1. And then the slope, things get multiplied by the year. So the very first time point, the time point in first grade, gets multiplied by 0. The time point in second grade gets a 1. Time point in fourth grade gets a 3. And then time point in sixth grade gets a 5. So with factors, we can basically create these intercepts. This is the intercept, and then this is the slope. So when we go through latent growth curve modeling, we're going to go through a few steps because, again, whenever we're in structural equation modeling, we need models to compare it to. So the first step, we're going to just say there's no change. We're going to say that the whisk for everybody, no, it's not changing. It's a flat line over time. So there's no change. This is the model we set up to knock down. This is our comparison model. It's probably not going to be the best model. We're using this as our sort of our null hypothesis. We're going to knock this down. The next model should fit better. Then we're going to allow a linear change model where things get improve, or it could actually go down over time as well. So it doesn't necessarily have to be a positive change, but there's going to be some sort of growth in this model. And then we can also, and I'm going to show you quite a few nonlinear change models, but we've got, things where we have a burst at the beginning and then, change sort of slows down over time. So we can have nonlinear patterns, and we're going to see if that fits better than the linear pattern. So we'll kind of build up these models to figure out which fits the data the best, how we can best predict everybody's trajectory. So the first model we're going to set up is an intercept-only model, or no change. It's going to be a straight line type of model. And I'll show you, this is what the results will look like. Everybody's going to get their own individual intercept, and we're going to say there's no change over time. So some people will start off lower, some people will start off in the middle, and some people will start off higher, but they're not changing over time. We're forcing this model onto the people. So how we're going to do this, we're going to set up a factor, and it's going to be indicated by each of these time points with a factor loading of 1. We're going to set these to 1. We're not going to allow m plus to adjust these like it would in a normal factor analysis. So if we look here, we've got our intercept is indicated by performance at first grade set at 1. So this at sign sets it at 1. It says m plus, don't touch this. We're going to just keep it at 1. Don't estimate this. Same thing with this second one. Performance in the second grade is going to be set at 1. Performance in the fourth grade set at 1, and performance in the sixth grade set at 1. So m plus really is not going to have much work to do in this model. It's not estimating these. These are all set at 1. What m plus is going to have to do, it's going to have to estimate this average for the factor. So this is going to calculate an average intercept. So in repeated measures, we just get the average. This is going to calculate this average intercept. It's also going to calculate this covariance, or the variance of this factor. and everybody's getting their own intercept. So there's going to be a variance associated with this factor. So that's going to be interesting because we're going to see all of the different places that people could start. And in that figure, we see this, there's a variance associated with this. There's a variance of where people begin. It's also going to calculate these unique factors, this residual left over, and M plus will do it automatically. M plus will calculate a different one for each of these. So we're going to actually tell M plus, and if you didn't put this in here, it would be fine, but we can think of these as all being equal. We think of that individual factor, because we're just creating an intercept, these are all going to be equal. So we're just going to say this next line here, performance 1, performance 2, 4, and 6. Go ahead and calculate it M plus, but they're all going to be one label, so they're all going to be one number. So when we get the output, we're going to see this residual variance, and it's just going to all be the same number. So this is the coding that gives us the same number for all of the variables listed beforehand. The other thing that M plus will do is calculate a mean for each of these. And so this next line just says M plus, don't worry about calculating the mean. Just we're going to set these at 0 because we don't want to waste any parameters, M plus guessing any parameters. So we're just going to say, you don't need to calculate what a mean is for each of these. We don't need that triangle to show that, because M plus would do it automatically. We'll just set these at 0, and that gets rid of 4 other parameters. So these two lines here aren't absolutely needed. They're needed to match up to multi-level modeling, and it takes away parameters that M plus doesn't need to estimate. So this is coded in here. We could get away with relatively simple code, but I've got this extra code in here just to make it, when we get into multi-level modeling, it will now line up exactly like multi-level modeling, and so that's why this extra code is in here. Again, when I've got this exclamation point, it's just a comment to myself, or comment to you, so you know what those lines mean. All right, and this is our output, and here is our output in the in the output file. We can see each of these are set to 1. So when we look at the factor loadings, so this intercept is indicated by each of these variables. It's set to 1. When we see these 999s, we know that it wasn't estimated, we set this to 1. These intercepts, this is where terminology gets a little bit confusing. I wish M plus just called these the means, but there's a reason it's called intercepts. But the means of these performance values are 0. We set those. That was that extra code that I gave. The variance of this factor, and to me this is one of the, when we get into multi-level modeling, we're going to talk about this quite a bit. The variance equals this number here. It's a big number. We'll want to reduce this number over time. We want to have less individual variance. The better we explain things, the less individual differences we'll have. So over time, that's something we're going to look at. It's part of the fit indices. And then the residual variances, I set all of these to be equal with that extra code that I gave. And so each of these are estimated. So each of these are shown here. These are those residual variances. They're all estimated to be exactly the same number, though. So that was the limitation I gave M plus with that code. All right, this is our fit indices. Again, this model is probably not the best model, and so we're just using this to compare to other models. So we're going to pay attention to this RMSEA. And we said before that when this is close to 0.05, it's a good fitting model. This is not close to 0.05, so this is a pretty bad fitting model. The AIC we'll use when we compare it to the next model. We want this number to be smaller, so with the next model we'll look to see if it's smaller or not. we can look at it for this model here, the CFI TLI. Again, we said the closer to 1, the better. That's not really close to 1. That's a bad fitting model. So our first model, we're kind of successful. This is what we'd expect. If we say there's no change, we're not seeing very good fit with this model. So we're going to go on to another model where we're going to say there's linear change, straight line change. So what we've got in this diagram, this intercept, we've already created this before. This is what we've seen in our last syntax. This is created right here in this line of syntax. So we're setting all of these to 1. We're telling M+, don't estimate these, set these to 1. So we've already done that part. We've also, I mentioned what these are in the last slide too. So we've done those parts. What's being added is this line of code, and let me fix that a little bit. This line of code, and what this does, it creates this extra factor. And so this, we're going to call this slope. So the slope is indicated by that first grade whisk performance set at 0. And again, I'm setting it at 0 so it will make our intercept make sense. When we get the value for this intercept, it's now set where kids were in the first grade. Indicated by this at time in grade 2 at 1, at grade 4 at 3, and grade 6 at 5. So these numbers 0, 1, 3, and 5 are pretty important, because what it does, it shows that from first grade to second grade, there's a 1-year interval, a 1-year jump. From second grade till 4th grade, there's a 2-year jump. And then from 4th grade to 6th grade, there's another 2-year jump. So we're setting these so that we're accounting for the different timings in the intervals. And simply, I just took the grade minus 1. So I'll say it even simpler. First grade minus 1 is 0, second grade minus 1 is 1, 4th grade minus 1 is 3, and 6th grade minus 1 is 5. So that's how we got those parameters here. And that allows for a linear slope, and it allows for those adjustments in change. So, or the different adjustments in timing intervals. So we didn't test everybody at 1-year intervals. We started doing it at 2-year intervals. It wasn't really me, but whoever did it started doing it at 2-year intervals. So that's represented by this part of the syntax. So still relatively easy syntax. There's this other component here. M+ does this automatically. I put it in here just to show this. This is the correlation between the intercept and the slope. This is really important, because this tells us where people start. Is it related to how people change? So if it is related, we can say that if people start higher, they change differently than people who start lower. So we're looking at that correlation between where people start and how much they change. So this is, to me, is one of the most important things that we get out of this that we don't get in repeated measures ANOVA. So we can see, are people who start off higher at a bigger advantage than people who start off lower, or the opposite, people who start off lower actually catch up to people who start off higher. So we want to see if there's a correlation between the intercept and the slope. And again, M+ will calculate this. You don't have to put this in there. I put it in there just to have that syntax in there. The other thing that I added is this plot command, and I'll show this in our workshop. But this gives us some interesting plots that we can look at. Again, not needed to run this analysis. All right, so what we want to do, we're building these models. We want to see, is this model a better fit than the first model? So here's our no change model. That was the intercept only. We had really bad RMSCEA. I don't know if I've ever seen it that high before. And I've run some pretty crappy models, but that's maybe a record. We've got our AIC. We're going to use that to compare. We want a lower number for the AIC. So when we look at it, when we look at our linear change, our new model, our RMSEA has gone to 0.201, much improved. We're fitting the data much better. Again, we'd like that number to be as low as possible, closer to 0, less than 0.05. Those are maybe ideal, but we're doing much better than we did when we said no change. And then when we look at our AIC, we also see a much lower number. So we're doing much better. We'll talk about a chi-square difference test later on, but we can look at where the chi-square is here with 12 degrees of freedom versus where it is here with 8 degrees of freedom. And we can say, did we significantly improve fit? And with a calculation in my head, we significantly improved fit. So we'll go over the chi-square difference test at some later point. All right, when we look at the output, the things that I wanted to point out was the correlation, or in this case, the covariance, it's not standardized, between the intercept and the slope, and that's significant. So it's saying that people who start off higher tend to have higher slopes. And again, the data that's graphed here is only 100 people. There are 300-ish people in the data set. So it's to make this a little bit easier to look at. So it's just 100 random people. But there is, I know of one person that looks very flat. So they start off low and their intelligence doesn't really grow. And then we see this person here who starts off high and grows a bit steeper than the average. So what this is saying, that people who start off with higher amounts of performance tend to grow even more. So the advantage, this is one of the arguments for preschool was that having this early education would help them grow faster, and people who might be left behind would grow faster with preschool. And I think, I don't know the literature that well on it, but that's been pretty well shown. So what we want to do is to get people up higher so that their slope is higher. So that's a big number that we can use for a lot of interpretation that we don't get out of repeated measures in ANOVA. The other piece is that the means of these values. So the intercept is 19, the slope is 6. So people start off at 19, and for every unit of change, they get 6 higher. So from 0 to 1, that's 1 unit of change, they get 6 higher. From 0 to 3, they should get about 18 points higher. And then 0 to 5, they get 5 servings of the slope. So I'm going to use scoops of ice cream in a little bit to talk about how many servings you get of this slope. And we can see here they get 0 servings of the slope, they get 1 serving of the slope, and then they get 5 servings of that slope. All right. What I'm going to do now is talk about some other ways we can look at this change. And again, when we have this model here, linear change, it's pretty good at talking about how people are changing. But that RMSEA, I think we can do better. So we're going to talk about quadratic change. And what this allows for is a nonlinear changing slope. So there's all these different patterns that we could see with a quadratic model, and I'll show you how to put this into M plus in a second, but we can see an escalating change or declining change, all kinds of different things. I don't use this method that often. It can be helpful in therapy though, because we might see a change pattern where people start off changing slowly and then speed up, or a pattern where people start off changing quickly and then sort of level off over time. So it can be useful in some therapy data. There's some other ways that I'll talk about to look at nonlinear change as well. So again, when we have our nonlinear change, we're basically creating a linear part, the linear slope, plus a quadratic part. So we're just using the quadratic formula, if you remember that from earlier algebra. So this is years squared, and I'll show you how to, in the next slide. This slide will make it more clear. So what we're going to do is, this is our intercept, which we've done 1, 1, 1, 1. That's easy enough. Our linear slope 0, 1, 3, 5. That's pretty easy to do. And then our quadratic slope, what we're going to do is take the years and square them. So 0 squared is 0, 1 squared is 1, 3 squared is 9, and 5 squared is 25. So that's how I get these scores here. And this is going to create that quadratic change in the model. So the one, and what I've done with the syntax is M+ has really changed the way that we write syntax. So earlier I was writing everything all out. M+ has syntax for these latent growth curve models that use this up and down line, and so you put in your different factors. M+ knows this is the intercept. The second one is always the linear change, and then if there's a third one, it knows there's quadratic change. So, and then you just put in the linear change at signs, and M+ knows automatically to do this. So maybe if you don't know how to square things or you're worried about it, this is a better way. This shortened version of M+ syntax might be a little easier to do things. All right, so here's that syntax. I could write it out in a different way and just be 3 lines creating each of these factors with these loadings. Yeah, that's in the plot. We had that syntax as well before. So when we create this model, and I create the individual trajectories using that plot, we see that there is a little bit of a different slope at the beginning, and it sort of levels off. So this, I didn't put the model fit in here. It's a little bit better of a fit. It fits the trajectory better. So that's good. It also is a little bit more complicated to talk about. It's much easier to talk about linear patterns, but to talk about quadratic change is a little bit more difficult. So we see performance, and especially if we take this out into older age, we'll actually see a pattern that you basically need a quadratic relationship. So we see people increasing, leveling off on performance or sort of fluid type of skills, and then as they get older, we almost see this decline. And I exaggerated the decline a little bit too much there, but those fluid skills start to dissipate as people get older. All right, this was something Jack McArdle created, and it's the latent basis model. So I talked about that slope getting scoops of ice cream, and we often set it up in a linear fashion, so you get 1 scoop, 2 scoops, 3 scoops, 4 scoops. However, nobody says that it has to be that way. We could let M+ decide for us how much of a scoop of ice cream that we get, or how much a scoop of slope we get. So in this example here, I've got, I'd say M+, this is the intercept, so this is what you're going to start with. You're going to give 1 scoop of change here. I set that, and then I let M+ decide how much the next levels get. So it goes up rapidly and then starts, goes up a little bit less rapidly. They get a smaller amount of change. So, this could be another nonlinear pattern, and this is something that I'll use more often to get at. We're allowing M+ to tell us what that pattern of change is. I'm going to go, let me show you in our example a little bit more. So here is that line of code. So I'm telling M+, start it at 0. So start that slope at 0, end it at 1. So this is when all change occurs, but then tell us how much change is occurring here and here. How much of that overall change they're grabbing at each time point. So that's really powerful because we're allowing M plus to estimate that. And when let me show you the figure. This is a much better. This is a better fitting model. So we see M plus saying there's a big change here. It starts to level off as time goes on. So we're seeing a bigger change at this point in time. So that's pretty powerful. And all we're doing is just saying, M plus, go ahead and estimate these. We'll give you a little bit more freedom back. We've been setting these and telling you what to do. Now we're going to let you have some fun with it. The other thing we can do, we can start looking at other predictors. So in this example with the WIS data, did the mother graduate college? So we can see, does this predict where people begin? And does it predict how much people change? So, and on the right here, I've got it figured out, kind of graphed. So we see it does predict where people begin. If the mother had finished college, the scores are on average about 23, 24. If the mother hadn't finished college, the scores are around 16. So graduating college for the mother affects where people begin. However, it doesn't affect their growth pattern that much. So these patterns are almost parallel, and so we don't have sort of an interaction. What we look for in repeated measures ANOVA is this interaction between time and group. We don't see that. These lines are almost exactly parallel. So this intercept, the effect on the intercept is significant. The effect on the slope is not significant. And to put this into M+, it's relatively simple. We're regressing these values onto a graduation rate. So that's how we get, that syntax is how we get these two lines. We can also decide, so the latent basis model that I pointed out, we allowed M+ to decide how much things are changing. We could have a slope that goes up and plateaus. So I could test the fit, and I've got a slightly different example here, but it's still the same principle. We could tell M+, hey, there's a big amount of change from time 1 to time 2, and then it plateaus. There's not going to be any more change over time. So that could be another model, and we fit that to the data. Is it a better fit? So now we can fit all kinds of trajectories and not just straight lines. Repeated measures ANOVA, straight line. This, you've got a lot of variability. A slope that goes up and then goes down. I can't think of an example right now off the top of my head, but we could have things that have a change pattern like this, and this might be the best fitting model. This data here is something we did with some substance use grant. We were looking at dual slopes and things that change and then change differently. So with the substance use grant, we're looking at different phases in treatment. So the first phase was giving them an advertisement, do you want to sign up for the self-help study? Then we did an assessment procedure, like, talking about their drinking, sent them the results. You're in the 90th percentile. You drink more than 90% of people. And then there was an intervention a few weeks later. So we wanted to see how much does just giving them feedback that they drink more than 90% of people change over the course of 3 weeks, and then how much does the actual intervention. So we allow for different slopes. So do people change more once they find out feedback that they've been drinking more than everybody else, or do they change more once we actually start the intervention? So these dual slope models can be quite useful. And then finally, the example that we talked about was pretty homogeneous. Intelligence, a lot of the slopes are pretty similar, but when we look at this data again, which is the slide I started, this is pretty homogeneous data. The individual differences in this figure are just really exciting. And we can look at predictors, what predicts people having slopes that are highly positive. And maybe it's a personality factor, maybe it's alliance with the therapist, maybe it's there's all kinds of things that could predict that. And then what predicts people who are not doing so well? And again, the same things could probably be the same predictors. It might be something different. Maybe it's another variable, maybe it's neuroticism or anxiety or something that causes them to be less happy. We'll get into in the next coming weeks is allowing M+ to find groups from the data. That maybe there's a cluster of individuals. The data is going to tell us who the groups are. These are superachievers. And when we find that group of superachievers, then we can look at what factors predict superachievers. So M+ is going to give us the groups. The data is going to tell us what are the clusters of groups. And here's another cluster of groups. And what predicts this group? And what about that group is unique? So that's going to be another exciting technique, because we can look at the data to find clusters of individuals.